We'll go ahead and apply this new distribution to a hypothesis test for a mean. Recall that the way that we calculate a test statistic in general is sample statistic minus null parameter over standard error. When the context is one mean, that sample statistic is always the same, it's just x bar. Our null parameter is the value that mu is set equal to in our null hypothesis, and so we would refer to that as mu sub 0 or mu naught. And then we also had an estimate of the standard error that we just got, which is s over square root of n. So when we put all of this together, we can get a nice simple formula for the t statistic that we use for a hypothesis test. The example we're going to look at is kitten weights, and the data set that we have here is weights in grams from a random sample of 10 kittens born from mothers who are what we call FeLV positive, the feline leukemia virus that they've tested positive for the feline leukemia virus. We're going to look at these data and address the question of whether kittens born to a FeLV positive mother have lower birth weights on average. So first we need to go into StatKey and enter these data, and we usually try to avoid manual entry of data. Since there are only 10 values here, it won't be too hard to just type these in. So we'll go to descriptive statistics for one quantitative variable, and the way that we're going to type them in is by clicking on that Edit Data button when we get to that page. So here in StatKey, under Descriptive Statistics, I want one quantitative variable. When I hit Edit Data, this whole list comes up. If I do a Control A, that selects everything so that all I have to do is hit the Delete key. I'm going to uncheck both of these because I don't really want to put in a header row, and I don't have any identifier. I just have a list of values. And at this point, I just need to type the numbers in, hitting an enter between them. So after typing all the values in, this is what it should look like. They shouldn't be comma separated. They should just be hit the enter in between any two values. So they should all be as a list with neither of these two boxes. First column is identifier, data has header row, both of those unchecked. Otherwise, it might misinterpret one of our data values as a label. So I get my summary statistics over here. I'm going to want these three. The sample size is 10, the mean is 92.5, and the standard deviation. I'll go ahead and take all three decimal places of the standard deviation. So that I've written down my summary statistics. Is it reasonable to assume that the central limit theorem applies? For that, I need to look at my sample size. My sample size is 10. If my sample size were at least 30, I could say yes here without really looking further, but it's less than 30, so I have to look at the shape of the distribution. This dot plot with a small sample like this, the dots are usually so spread out that it's hard to really get a grip on the shape. I would come over to the histogram and maybe decrease the number of bins a bit since we only have 10 observations anyway. It does not look perfectly symmetric. It looks like we have a bit of right skew here, but not an extreme amount, and we don't have extreme outliers. So we're really iffy on this, right? We'd say maybe the central limit theorem applies, but not necessarily. For n equals 10, we might like to see a little bit more regularity and symmetry in our sample. However, if we look at the histogram and even a box plot again, we can see that there are no outliers in this sample, and so it might be reasonable to proceed. Sometimes when it's not totally clear, we just say proceed with caution. So coming back here, if I go to the box plot, I can see that there are no observations that were identified as outliers. So this answer in the process of answering a question like this is what we also often refer to as checking conditions. When we talk about checking conditions for using t-distribution, we're referring to this. Does the central limit theorem apply? Is it reasonable to use a t-distribution for inference here? All right, so according to the ASPCA, kittens typically weigh approximately 100 grams right at birth. So we're going to investigate whether average birth weight is lower among kittens born to a FeLV positive mother cat. My null hypothesis is that they are the same. That in fact the mean mu of all kitten weights born to a FeLV positive mother is still 100 grams. The alternative hypothesis is that the birth weights are lower, so that mu is less than 100. Next, we'll calculate a t-statistic for these hypotheses and for our data, and remember that our t-statistic follows this formula here of our sample statistic minus the null parameter divided by our estimate of the standard error. Also recall that we wrote down some summary statistics, and we have that our sample mean x bar is 92.5. Our sample standard deviation S is 9.656, and N, the number of kitten weights that we have to work with, is 10. So our t-statistic is x bar, which is 92.5, minus mu naught, which is 100. That's mu under the null hypothesis. And this will all be divided by S, which is 9.656, divided by the square root of N, which is the square root of 10. Now we can put this into a calculator, but something you have to really keep in mind is that this whole denominator needs to go into parentheses when you put the expression into your calculator. Alternatively, you can just evaluate it first and put in a nice standard error estimate that's out to about 4 decimal places. But if you plan to evaluate the whole thing at once, put that denominator in parentheses, because it's the way to get your calculator to follow the correct order of operations. Your t-statistic will come out way off if you leave those out. So here's how I'm going to evaluate this. 92.5 minus 100 gets me negative 7.5. Now I'm going to say divided by, and I'm going to hit this open parenthesis, 9.656 divided by 10 square root. This particular calculator takes the square root of whatever is on the screen. Now I enter my close parenthesis, and now I hit equals to get negative 2.456. Note that what the calculator is going to do if we don't use parentheses is it's going to tend to do the numerator divided by this number, and then it's going to divide the whole result by the square root of 10, which is going to be very different. It would have the same effect as really multiplying the denominator by the square root of 10 instead of dividing. So if you're not sure, the other way to do it is just to do 9.656 divided by the square root of 10 first. And we could do that in a calculator, right? 9.656 divided by 10 square root. That gets me 3.053. And then we could plug in and say negative 7.5 from the numerator divided by that 3.053. .5 negative divided by 3.053 gets me that same value of negative 2.456. So this is another way to do it. Is just calculate the standard error first, which is really what we mostly do with confidence intervals anyway. Okay, so we have a t-score of 2.456, and how many degrees of freedom in the distribution? Remember that we always use n minus 1 when we're working with one mean. N minus 1. So n in this case is 10, and therefore we would say 9 degrees of freedom. Now the way we use this table is that we first look up the correct degrees of freedom over here, and we see that this is 9. And so I'm going to look at the whole row corresponding to 9 degrees of freedom. Now I'm going to try to locate where my particular t statistic sits in that row. 2.456 is really between these two. The fact that my t-score is negative doesn't really matter. That just indicates I really have a negative t over here. I'm still just looking up the absolute value of my t in this table. So I'm going to look up t equals 2.456, get that it's between these two values, and that tells me that I am just looking at options between these two values. Now from there I need to still determine what row to look at to get my p-value, and that's where I decide whether I have a one-tail or a two-tail area that I'm interested in. I have to look back at my alternative hypothesis for this. My alternative hypothesis is that mu is less than 100, and that tells me that I want a one tail. This is a left tail. But for the purposes of this table, all I care is that it's one tail. So the row corresponding to one tail is this one, and the intersection of everything, well, you go ahead and use red to make that really stand out. The intersection of everything is these two values here. These correspond to one tail area and to the t critical value that we have here, which we know is between these two, or rather our t statistic, which is between these two t critical values, right? So my p-value is between these two values. It's between 0.01 and 0.025. Remember that the table just gets you bounds on the p-value. It doesn't get you a really precise p-value. We can use StatKey to get a more precise p-value here. But the table gives us enough information to draw a conclusion. So let's go ahead and write down what we think our approximate p-value is. The p-value is between 0.01 on the low end and 0.025 on the high end. And let's also go to StatKey and get a more accurate estimate of this after we draw a quick little picture here. In my picture, I need to have my null parameter in the center. My null parameter is 100. That's mu naught. And my sample statistic is where the tail starts. So my sample statistic is 92.5. I'm drawing it pretty far out because my z-score was, or my t-score was 2.5, so we're approximately 2.5 standard deviations less than the mean. It was negative 2.5. And so this is what my tail area would look like for this p-value. To get this p-value in StatKey, we'll go to Theoretical Distributions T, enter the 9 degrees of freedom that we decided this model has, and then left tail, and type in our t statistic of negative 2.456. And we can see that the p-value is 0.018. So when we're doing homework problems in Wiley Plus, we need more precise values. We'll go ahead and get those p-values from StatKey, but feel free to get as much practice as you need with this table, because the table is what you're going to have access to on exams. It's also worth mentioning that there's a lot of this table missing in the handout. We didn't want to necessarily take up a whole page of the handout for the table. So where you see this ... here and this ... here, that's missing rows from this table, but those rows are filled in the full table, which you'll find in Blackboard. In Blackboard, you can find a link to Table A under Handouts. Table A. You can see it starts with this normal table, and then on the second page we get into the t-distribution, and we have rows for lots of different degrees of freedom. If your degrees of freedom don't exactly match one of these rows, you can see once we get to 30 here, we start jumping up by larger amounts. If your degrees of freedom don't exactly match one of these, just take the closest one. It doesn't matter. Between 50 and 60, you can see that these values, these critical values, only differ from each other in the thousandths place anyway. And once we've gotten above 100 degrees of freedom, we almost may as well be using a normal distribution because we're already pretty close at that point. So you're not going to get super accuracy using a table, but you will be able to get a pretty good estimate of your p-value. And we can see that based on our p-value at the 0.05 level, because our p-value is smaller than 0.05, we would reject the null hypothesis and say that we have statistically significant evidence that kittens born to a FeLV positive mother have lower birth weight on average than that 100 that is believed to be true for kittens across the board. And here's our conclusion. We have statistically significant evidence that the mean birth weight of kittens born from a FeLV positive mother is less than 100 grams.